Welcome to Summarize Science. Today, we're looking at a fascinating challenge in the world of brain-computer interfaces, or BCIs. These devices read your brainwaves using a technique called EEG, allowing you to control computers or prosthetic limbs with just your thoughts. But there's a big problem. Everyone's brain signals are different, and sometimes they can be so strong that they overwhelm the sensors. Traditionally, when a signal is too strong, it gets clipped, meaning the top of the waveform is simply cut off. This is a huge issue because that clipped part contains valuable information that is lost forever. To solve this, researchers developed a clever technique called modulo sampling. Instead of clipping the signal, the sensor folds it back around, sort of like how a tape measure wraps back to zero once you reach its end. All the information is preserved, but now it's jumbled up, and the challenge is to accurately unfold it back to its original shape. In this paper, researchers from the Indian Institute of Technology Kharagpur propose a new AI model to do exactly that, and they call it GraphUnwrapNet. What makes their approach unique is that they don't just see the EEG data as a collection of individual signals. Instead, they view it as an interconnected network or a graph. As you can see in this diagram, each sensor on the scalp is a node in this graph. These nodes are connected to their neighbors in space and also to their own previous measurements in time. This structure allows their AI to understand the context of the signals, knowing how different brain regions are working together. They also added another clever component called a pre-estimation guided feature injection module, or PGFI. Think of this as a helper AI that gives the main network a rough estimate of where the signal has been folded. This cheat sheet helps the main AI focus on the trickiest parts of the signal, making the unfolding process much more stable and accurate. So, how well does it actually work? The researchers tested GraphUnwrapNet against several other methods, and the results are quite impressive. Looking at this table, we can see that their proposed method consistently achieved higher accuracy and a better correlation with the original, ground truth signal. For example, at a folding threshold of 0.60, their method was over 3% more accurate than the next best model. They also ran a test where they removed that special PGFI helper module. The results, shown in Table 2, clearly demonstrate that performance dropped significantly, proving just how important that pre-estimation step is. So, let's quickly recap what this all means. The way we currently measure brainwaves often leads to lost data, which limits the potential of brain-computer interfaces. The new modulo sampling technique saves this data by folding it, but it requires a sophisticated method to unfold it again. This paper introduces GraphUnwrapNet, the first AI model of its kind to treat EEG signals as a connected graph to solve this unfolding problem. Its success could pave the way for more robust and affordable EEG systems. This could lead to more reliable BCIs for people with disabilities, better tools for monitoring cognitive workload, and a deeper understanding of the brain itself. It's a fantastic step forward in making mind-reading technology a practical reality. Thanks for watching Summarize Science.